In this example, I'd like to consider tension compression bar of length L with cross-sectional area A and Young's modulus E, all constants, and applied force P at a distance A from the support. And what I'd like to do is compute the deformation at x equals A in terms of the force P. And I'd like to do this using conservation of energy. So it's a linear elastic system, so the work in is 1/2 P times the motion I'm interested in, delta. And the work stored is the elastic strain energy. And we have two options. We can write it in terms of kinematic quantities, or equivalently, we can write it in terms of kinetic quantities or forces. So 1/2 r squared, the internal force, over AE dx. And the version that you use, either the kinematic expression or the force expression, really depends on the problem at hand. So whatever it's convenient to determine for the integrand, we're going to use. So in this case here, we're going to go ahead and use the force formulation because it's easy to know what r of x is. And so for this problem, simply from statics, r of x is equal to p for x between 0 and a, and it's 0 for x between L and A. So my integral for the work stored really is just an integral from 0 to A of 1/2 p squared over AE, which is equal to 1/2 p squared L over AE. If I set the work in to the work stored, in other words conservation of energy, then I see that I have 1/2 p delta is equal to 1/2 p squared A over AE, and so there's an error down here on my integral. That should be p squared A, and so the halves, 1/2 cancels, 1p cancels from each side, and my final answer then is delta is equal to PA over capital A E. So that gives me the relationship between the applied force and the motion that occurs at that point.